Good afternoon, everyone. It's my great pleasure to introduce you to Dr. Xiuzhe Luo, who recently finished his PhD from PITP and University of Waterloo. And Roger is soon joining a quantum startup company, a spin-off company from Harvard University, QuEra, as a research scientist in the fall. And Roger describes himself as a physicist during the day and the software developer during the night. So yeah, without further ado, let's see, what interesting story Roger is going to bring us.
Okay, thanks for the intro. So today I will talk about recent work we had that is trying to generalize Wilson's energy and Xiuzhe energy from the perspective of machine learning, and also seeing this two algorithm as a very special compilation algorithm between two representations. So before going to the details, I would like to talk about some observation and introduction, like some inspiration first. So to give you some motivation why we care about such a generalization. So first of all, we want to know what problem we're looking at here. So we're more looking at the very general simulation problem in a fundamental model system. So that is talking about given a geometrically k-local Hamiltonian H, defined as sum over some k-local Hamiltonian terms, and all local observable O, and initial state rho 0, and we want to compute the expectation value at complex time t. So this basically the definition of all the simulation problems, including ground state problem, imaginary time evolution, dynamic real-time evolution, or even open system. There have been some theoretical results saying that this problem is very hard. It can be even hard for quantum computers. Some instances can be Q-sharp, can be QMA complete, but we also have so many observations in practice. So if you do numerics or you try to calculate some system, maybe you would also use this property that if I run like a DMRG algorithm or like some others numerical simulation algorithm, how do you know your 100 size simulation is correct? Because there's no guarantee that this is converging at that. So usually people will do is I will also run 102 site and 104 site or 101 site, and to see if there's a consistent behavior between different scales. And this is mostly because the system is local. And here's an example of real-time evolution of a 1D transfield Ising model, exact simulation at different time but with different number of sites. So as you can see, it's not at the detail scale, it's not really very easy to see what the behavior that is, but at the rough scale, it's not when you rescue the system, it's not jumping like to some random place. It's still within some nearby range. So theoretically, we know that this is usually because in real-time dynamics, there's a Liouville-Robson bond that your information or your change of local observable values cannot propagate outside a LightCom. There's a fixed speed of propagation of such information. And if you look at some more special cases, actually can be more obvious. So here's the ground state energy of transfield Ising model of 1D, and this is even linear of 1 over the scale. So now if you are from just machine learning community, so you don't know physics, but I ask you to predict the property by looking at these numbers. these are very easy to predict, right? It's even linear. You can do it by your eyes. So this indicates something that's if we don't solve the original simulation problem, we can try to solve a different one. So what if you're given an oracle access to all the observable from 1 to n-1 side to query any observable expectation you want? Maybe solve the simulation problem as n-side system will be easier. So we want to see if there's someone actually think from this direction in history. And it turns out that back in 1975, Wilson already did so. So he was trying to solve the Kondo problem using the renormalization group. If you don't know what is renormalization group, is fine. I'll go over the procedure here. So basically, we want to solve a very large quantum system. Here we want to, but we only have small system solvers. So we first divide the quantum system to some small blocks noted here. What Wilson was interested in is the low energy spectrum of the large system. He wants to know the behavior of the gap. So what next we can do is we can try to truncate the Hamiltonian representing these blocks, these two-side blocks, to some smaller space, which give you a virtual Hamiltonian that is a smaller matrix, but it preserved the low energy spectrum, right? So you can do a projection here and make sure the projection preserves the low energy spectrum. And then we can believe that this new Hamiltonian, which is a smaller Hamiltonian, is a good representation of this two-side system. And then we can use this Hamiltonian to build a slightly larger block, which contains four-side system, which give you a double-sized Hamiltonian of describing four-side system, and we can do this truncation again. So if you iterate this process, in the end, you will get still a trackable size Hamiltonian matrix, but describing the large system or infinite system. And by guarantee of your optimization in the middle, guaranteed by your optimization procedure in the middle here, you should be able to preserve the low energy spectrum. So then in the end, you output your low energy spectrum as a prediction of the large system low energy spectrum. So this is basically the most basic setup of RG. But later people find this actually have some problems. Well, this works very well on the Kondo problem, but if you try to apply this method to a slightly more quantum problem with more quantum interaction, you will see that this method is having a hard time predicting properties on the boundary. Your eigenvalues shifting will be shifting a bit more. And on the other hand, if we don't really care about the low energy spectrum or the gap, what if we just want to calculate observable on ground state? If you look at loss function here, when we say projecting to low energy subspace to preserve the low energy spectrum, this is basically saying we set a loss function that is the error of low energy spectrum. But if you want to calculate the observable on ground state, this is not an optimal loss function. You should define a loss function as the error of the observable on ground state. So to fix these two problems, in 1992, Steve White generalized Wilson's NRG to fix these two problems by first introducing the superblock description to mimic the boundary behavior. So how this is done is instead of just looking at a single block, we now insert a physical side on the boundary of your block, and then we see this thing is a system, and we mirror this on the other side to mimic the behavior of an environment. Because if we're trying to calculate an infinite system, your system is always inside inside some bag. So so we call this this entire the entire block is called a super block, which contains a slightly more complicated structure of the system, but it turns out it can mimic the behavior of, it can model the behavior of boundary condition very well. Unlike Wilson RG, that you only need to keep track of the Hamiltonian matrix, because now we need to build a super block which involves a few other operators. So you also need to keep track of a few other operators matrix that is relevant in your calculation. And next we basically do the same thing as Wilson RG, where but instead of projecting into the low-energy set space, we first solve the superblock system using some exact solver. We get the ground state of we get the ground state of the superblock, and we trace the environment away. So we get a description of the ground state density matrix of the system, and because now we care about observable on the ground state, so we basically want our projection to be some projection of the ground state density matrix. And and this in theory will be the optimal projection will be found as the principal components of your density matrix. Right, so then this projection will be your, or in other words, this is called Schmidt equalization of your density matrix, and this will be the projection from your density matrix. So this projects your operators into a chosen state subspace. So in more general setting, the states you pick here does not have to be ground state. Well, in most cases, people do ground state with DMRG. So you might find this explanation of DMRG is very different from today's DMRG, where people trying to explain using tensor network setup. But this most original idea of DMRG from 1992 is exactly where we start our generalization.
Sorry.
Uh-huh.
How do you define super block? Does it need to include all the sites in environment, or environment is always doubling the system size?
Yes. This is describing the infinite DMRG. So environment is always the same size of the system.
And is this always enough to incorporate the boundary conditions?
Yes, for infinite DMRG, for 1D infinite DMRG, this at least practically always enough to cover mimic the boundary.
So you see that where the boundary conditions are included in the white scheme versus Wilson scheme.
Yes, so here you basically mimic the boundary by adding these physical sites, but in Wilson scheme, there's no boundaries condition being dealt with.
But presumably you can use bigger block in Wilson.
But you cannot. The problem in Wilson's RG is because you basically assume there's no interaction between these two blocks. So that is where.
When you analyze it in the smaller subspace for the bigger block, don't you have interaction with the Hamiltonian?
When you grow the block, you don't have a good description of this interaction.
But then what's the point of adding the two blocks? That you projected the two sides, projected to other sides, and then you create this bigger block with 4 sides. But if they don't interact, what exactly are you doing?
I mean, that is basically why Wilson RG only works well for Kondo problem. Like if you try on T-film, it doesn't work. It doesn't work at all.
But I thought you were reducing in the 2-side problem from like number of states, and then you can combine two side to the bigger block, and diagonalizing a bigger block.
But
you're saying that there is no interaction between the.
There's a very weak but like here if you look from the DMRG perspective, it's missing a few interaction terms when we combine the blocks back.
So in Wilson's, there is no interaction between these two sides.
Well, you can still see there are interaction, but it has to be very weak.
Why does it have to be very weak? You rediagonalize it anyway.
Well, to the best knowledge I know, I don't see any like very good theoretical explanation, but I think in practice, people find this gives you much better results, and the original setup, which does not count these interactions, like a site interact with a block. This kind of interaction does not appear in the Wilson RG. So so in practice, basically Wilson RG does not work for more quantum systems.
Okay.
So what we have so if we look at the DMRG and RG setup, and we can see the setup itself is very general. It's not really limited to 1D system. But in today's world, we all know that DMRG is very limited to 1D system, and in higher dimensional system or random connected system, you suffer these so-called exponential bound dimension problem because the underlying state DMRG solves is a matrix product state, which will have a bound dimension grows exponentially, but also, let's look at this setup. Is the general formulation of a numerical renormalization group is not 1D specific. So we want to see what's the problem causing such discrepancy. So from some recent results from the machine learning community and also condensed matter community, that we kind of see. It's more because the operator maps we have been using in DMRG and NRG are linear, and linear maps are very limited in expressive power. So one result I want to probably highlight here is the theoretical proof that if you want to approximate a 3-layer neural network with a 2-layer neural network, it takes exponential number of parameters to do so. And there are also a few more results to discuss the expressiveness power between a tensor network and a nonlinear map. So we see that if we can generalize the operator map between these RG scheme, then we will have the hope to resolve this exponential growth bound dimension problem. And more generally, we can see the DMRG and NRG scheme as we start with a real system. We map the operators in the real system to some operator as a virtual to some operator easier to simulate or easier to run as a virtual system, and then we grow the virtual system to a real grow the virtual system to get a new real system that describes a larger system, and then we do the operator map again until we get a virtual system give you the description of the large system. So if we can generalize operator map to an arbitrary function, it does not only solve the expressiveness problem. If this is an arbitrary map, then your description of the operators in the real system does not have to be a matrix anymore. It can also be other representations, such as a POS program that actually controls a quantum computer. So this will give us a chance to not only lead us to better classical numerical simulation algorithm, but also give us the opportunity to have to derive a DMRG style quantum algorithm. So, so in general, big picture, overall picture of our work, we named operator learning RG is we try to develop a theory framework to generalize the NRG and DMRG from the perspective we just discussed. And you can use arbitrary operator map, and you can use arbitrary operator map as your projection function or your transformation of the operator representation. And unlike previous variational algorithms that optimizes energy or the norm of Schrodinger equation, we directly optimize the error of your observable. So this is the first end-to in machine learning community's world. This is the end-to-end machine learning algorithm, which means you skip any intermediate targets, directly optimize your error of target. So the benefit of this is when optimize energy does not always necessarily give you a ground state when your energy gets minimized, because that is not your target. So what usually happens is your energy has to be 10 to the negative 6 to get the error of your observable at 10 to the negative 3.
Sorry, so you were talking about the complexity of operators, if I'm not mistaken. But the operator is usually relatively simple in many body problems like Hamiltonian, let's say. Right? So why do you need more complex representation for the operators? I thought it would be more reasonable to have maybe more involved representation for the wave function.
So if you look at the setup of NRG and DMRG, there's no explicit wave function.
Right, but there's still states that you are.
So we're generalizing this map.
So that's for the.
There will be an implicit state, but we're not trying to model a state. We're trying to see how can we make this process more expressive.
And currently, it's not expressive enough for high-dimensional systems.
Yes, because we see that this is in previous setup, this is linear, which is nice because you can directly solve the optimal point. But linear maps also is very limited in expressiveness. So we see this is we're causing the problem of exponential growth bound dimension in DMRG, right? So because you need more expressiveness to express more complicated system, and the only thing you can do is to increase the size of the map, which is the bound dimension. And what we're trying to do here is we want to generalize based on the DMRG and NRG to develop this spherical framework that allows you to do arbitrary map. And because how RG is set up, so it becomes operator map instead of a state. But I will come back later that you can see the connection between this and the existing state-based method like TDVP. In some special case, we'll fall back to this method, and you can write down an explicit state. But we from now on, we will all work inside Heisenberg picture.
So essentially, by operator, you mean the density operator, roughly speaking, right? So that's what you want to parameterize.
We're trying to parameterize the operator relevant to your calculation, not only density matrix. There's no explicit state in the setup.
I would say this X and V, dagger X, V, those are the states.
Essentially, you can think V is a state if the operator map is linear.
Well, V is a projection, right? So you're taking a particular subset of the decomposed density matrix.
Yes, you can think V as a state if you connect all the V's together. This is the V of first RG step, the V of second RG step. So these are the V's in DMRGO NRG process. So you connect them together and you look from this side, this is MPS, which is a state. But if you generalize them from in our theorem framework, this does not necessarily to be linear. So you can't always write down an explicit state. So we're more thinking from the Heisenberg picture. So basically, this is actually a sentence from our paper. If you think about what you want in the end, you just want some value of observables expectations. So you don't have to model a state. So, the point is, I just want to figure out a way to find those a few scalar values of these observable expectations. And in programming community, there's a saying: if it quacks like a duck, walks like duck, swims like duck, it is a duck. So if I can find a set of operators that produce similar expectation values, I will think there's a description of the original physical system. So we're trying to find a new set of operators that is easier to keep track of, but still predicts this, give you the same expectation value.
How do you know is it the same or not if you don't know the value that you're looking for?
That's our theory is about. Okay, so this is what.
Sorry, just another question, like an advantage of TDVP or something is that once I have a converged wave function, I can then measure, in principle, any observable I want. I can measure entanglement spectrum, do such things.
Yes.
Do you have a similar, do I need to re-solve this for if I want to do SZ versus a different observable, or?
That's a good question. Actually, Mouse asked exactly the same question like half a year ago. And we managed to figure out a way to not rerun the whole, because the nice thing of, well, this is the advantage and disadvantage. Advantage is we directly optimize towards what we want in the end, but the disadvantage because there's no explicit state. So either we cannot pass the state to the next time point, and we cannot measure other things that you were not prepared to solve. But later we actually find that you can actually do something called transfer learning. That is also a generalization of DTDVP that allows you to also solve other values with very cheap cost. So if there's no more question, I'll go ahead and actually explain how this works. So first to know how this will work, we need first to understand how DMRG works in 1992. So we cannot use the tensor network to explain DMRG here because it's very critical to understand the physics intuition back in 1992 to do this generalization. So first of all, let's look at the workflow of infinite DMRG, which keeps growing the system. So I will not talk about finite system DMRG, but if we have time later, I can also explain what that looks like in this picture. So the workflow of DMRG, as we talked about at the beginning, start with some super block setup. So here I would notate it's a description of free size system as S3, and 0 means it has the description of this system has not been modified. So now you apply this basis transformation in the MRG to truncate the system operators in the system to some operator in a virtual system that is have smaller matrix. So here we annotate the map of the operator map as f theta. In the MRG case, that is your basis transform. And it transform your three-side system to another three-side system that has been modified once. And next step in the MRG, we grow the system by one side. We grow the system by one side. So it gets a full-size system here denoted as S41, which means tracing back, it has been this set of operator describing the full-size system has been modified once. So similarly, we repeat this process that in the end we output a five-size system that had been modified twice. So if we want to generalize this process, basically we're talking about we want to generalize f theta to an arbitrary map. So a most naive approach is we have been talking about this swims like a duck principle. So basically, if we want this, we basically want to preserve the some property we want. Assume our property function is a p. That output maps these that calculates some property from the system. We can just see we can define a loss function here that is the error of the property before and after your f theta map, and maybe it will be solved. So however, we actually try this numerically. It turns out it does not necessarily to bound your final prediction error. The reason is the discrepancy between the neighboring the map at each same number of sites does not necessarily guarantee the error of your final prediction and your ground truth. So if we write down the write down the system of each growing column. So on the leftmost column, this is your ground truth, and the P(f(5)0) is what you want to calculate. And this column has been mapped once, so this is P(s)(5)1). That is the so if you can keep growing this together to get the P(s)(5)1). And here P(s)(5)2) is your prediction. So what we want to do is to bound the error of P(s)(5)2) and P(s)(5)0), which is a ground truth. And once you draw this diagram, it's more obvious that if you want to bound these two, all you need to do is to bound the error of neighboring columns. We call this the scaling consistency because you're not just guarantee your local scales to be consistent. You also, when you do a map of your operators from the three-side system, you also need to guarantee its expectation value needs to be consistent across the scales. However, now we reduce the problem to a single RG step. We still cannot calculate this loss function. We need to find a trackable loss function that we can calculate in a local system. Because here you can assume this is a very large system. So first, before we look into the actual theory of how what the loss function is, we first let's look into the growing procedure. How you exactly grow in larger system. So this is inspired by that matrix embedding theory, where if you want to grow, we need to divide the system first. Otherwise, it can be ambiguous when you grow the system. So I will skip more details. Here I'll give you some example directly. So you can grow a product state. It's very easy. Just multiply with another product state. You can grow a Hamiltonian. Here's an example of transfuel-Ising Hamiltonian. You can rewrite a Hamiltonian as the Hamiltonian of the n-1 size plus some interaction term. And you can grow the two-point correlation functions in this way that basically you cut this two-point correlation into some small pieces and put them back. In the most general form, the growing operator can always be written like this. So it always contains an operator on the boundary of your system and another operator paired up on the growth part. So we call the one on the boundary operator, and the operator paired up with the boundary operator, the connecting operator. So this describes when you grow an operator how the interaction happens. For Hamiltonian, or like a 1D system, if you're familiar with tensor network, it's actually just a tensor inside an MPO representation. So now we can look at a more specific problem to understand how can we reduce the problem, reduce the loss function calculation to a local system. So first of all, we assume that we're looking at the geometric local Hamiltonian, and if we keep growing a Hamiltonian, because it's geometrically local, we'll keep applying the growing operator many times. Eventually, at some point, it will saturate. But so only terms inside this yellow band will have interaction with your system by definition of the locality. So that means your growing operator must be equivalent to some special growing operator. Where the terms the connecting terms are only from this yellow band. And secondly, assuming this is our final property we want to calculate, if we can expand them into some Series expansion, such that it's a Series expansion of observable values, where AI are on the system and the BI are on the rest of the system. So by definition of our F beta is operator map applied only on the system. So only AI has been modified. So then basically, if we can have a loss function, minimize the discrepancy of AI prime and AI as our loss function, we'll get this. As long as the rest of the series this series converge to a constant, then we can guarantee that if you optimize this loss function, this will lead you to minimizing your target property error. So now our task becomes, how can we find a series expansion looks like this? So in order to find the more specific series expansion, we need to look at more specific problem. Here we look at time evolution, predicting a time evolution of an observable. So where the property defines this. So you start with some state. You evolve the operator, the observable operator by some time. We assume the initial state is some simple state that we assume it's just a product state. So we find that the series expansion turns out to be a variant of Dyson series under the Heisenberg picture, and the A's are actually some correlators with the boundary operator. So here's a few example of the first 3 order of these correlators. We call them time order boundary correlator. And the zeroth order correlator is exactly the naive loss function we proposed initially, so which explains why it sometimes work. So to give you some, so more generally, if you're able to optimize these correlators area to be an epsilon, then your target observable area will be upper bounded by this upper bound. So we're not claiming this is to be a very tight upper bound. Otherwise, we see that this can be further improved. But this bound tells us that if you can optimize epsilon, the error this will be optimizing the correlator is equivalent to optimizing the error at large scale. So to give you a feeling what this correlator looks like, so here we do some exact simulation to see what the correlator looks like across the time axis. So the x, y axis are the time parameters in the time order correlator, and the heat scale is the absolute value of the correlator. So you can see many correlators are exactly zero, well, which actually indicates our bond is a very loose bond. Definitely can be improved. And some correlators are non-zero and looks like have some nice patterns, which we believe is due to some symmetry. But now we know what the loss function is. And we can basically calculate this loss function and run some algorithms. So I'll skip the steps. Go to this result. So basically, because now we can use arbitrary operator maps, we can also use, for example, a neural network. And we try this. We try to see if our theory is correct. Here is numerically, and here's like a 10-side system grow from a 3-side system, simulating 1D transfield Ising model dynamics. The dashed line are the exact results, and as you can see, the naive loss function, which is order 0, is not able to bound the error at a longer time, but second order and third order loss function is already sufficient to keep bounding the error at a longer time, up to 10 to the -3. And if you increase the depth of the neural network, actually can improve the performance at longer time, and here it can even get to around 10 to the -4 error, relatively error. Next, because now the operator map is not a linear map anymore, we can also see the operator map is a map from your problem Hamiltonian description to a pause program. So then the step becomes, if we don't seek for optimizing truncating operators, we're looking for what is the corresponding control parameters on my quantum device that can reproduce the same dynamics of my problem Hamiltonian. So we basically need to find a different Hamiltonian on the device that reproduce same dynamics, but all other operator does not need to be modified. So our operator map is only our map on the Hamiltonian, and it is identical to all other operators. We call this the Hamiltonian expression map. So we start from, so this can be done in this way. So start with a simulation which predicts these correlator values of the correlators. And we also have quantum circuits that also have some control parameters trying to produce the correlators. We first optimize the control parameter in this quantum circuit with N0 size to match the correlators in the simulation. And then we can grow the quantum circuit based on the definition of our growing operator. This will give us a quantum circuit look like this, where the blue gates are analog, are some large already compiled quantum gates or analog quantum circuits, and B1, B2 are local gates, digital gates that describes the correlation. And then we can use this circuit to calculate the correlators. We can use this to calculate correlators, and then we have another analog circuit or just or some parameterized circuits that contains the a bit more control parameters with n plus L size, and to match the correlators produced by this circuit, and then iterate between these two circuits until we reach a target size. So this allows us to use a small system control algorithm to control a very large quantum system in the style of the MRG. And we also try this with simulation, but due to limitation of our simulator, we can maximally simulate 6 sites, but we try this from growing from 2 sites to 6 sites. We'll see that all the zero loss function fails to bound the error at all, at longer time, as similarly all the one also cannot bound the error. And also see a consistent bump in the middle for order 2 and order 3. We kind of suspect this is because our ansatz we're trying here is a global Ripper Hamiltonian, which is now technically a universal Hamiltonian, so it cannot represent the whole dynamics. And actually, to answer the question asked earlier, how do you so we can predict a value at some target, but we cannot. How do you calculate? How do you scan other values? For example, like in TDVP, you have an explicit state, then you can measure whatever you want, and also TDVP pass explicit states between each step, so you can basically scan the time axis easily. So we find in our setup, all you need to do is actually do something like transfer learning, basically just reinitialize your next calculation with previous calculation parameters, and this reduce the training epochs a lot. Basically, here is only by 500 epochs per point, which is way faster. And we find that this does not only solve the problem that you can calculate other property values, and this also improves the performance of different orders of loss function. And here is above this dashed line are the points gets improved comparing to directly solving it. We kind of see why this happens because by choosing a good initialization, you actually pass the state implicitly. So comparing to time-dependent VMC or TDVP, that's actually this fallbacks to them when F beta is linear. So it's fallbacks to MPS TDVP, where you can write down explicit state as MPS, and the reinitialization step is basically passing the state. So we see that our setup lines up nicely with previous theoretical framework. So we see that previous theoretical framework is a special case of our framework. And to conclude the talk, we introduce a general formalism and theory guiding design of loss function, and we see the loss function can definitely be improved in the future by tightening the bound, and also introducing more heuristics. And we believe we're the first version of framework that introduced end-to-end loss function that directly optimize your error. And unlike optimizing energy, we don't ask you to optimizing the loss function to 10 to the -6 to get a 10 to the -3 observable error. Whatever you optimize is what you get. So we don't have like gradient vanishing problem. We don't have error bias. So this is what we learned from machine learning community. And next, we are able to use differentiable programming. I was expecting someone will ask a question, but I will ask this myself. So f theta here actually, the f theta we talk about here actually, it can be the same f theta. It can also be the different f theta. If f theta is linear, which is the traditional DMRG case, it has to be different because of the expressiveness is very limited. You have to just do use a different ansatz to model the map. And unless your system have a strict translational invariant, otherwise f theta has to be exactly the same. But in our case, if you have very expressive f theta, it can be the same map, no matter if you have translational invariant or not. And actually, what I just showed in our numerics is the same neural network used across all the steps. So you use way less parameters than a traditional MPS. And this is also possible also because the differential programming allows us to differentiate through a exact solver. We are trying to match the correlators between the neighboring columns. So last we see that this also introduced a new category of ansatz, which is not a state ansatz anymore, but operator map as ansatz. This is also a new category of ansatz that has not been explored before. And in this work, we explored the operator matrix map and Hamiltonian expression map as the two of this kind of ansatz. So I will skip the outlook. Thank you.